This is my video on Lab 3 where we'll be dealing with circuits. The goal of this lab is to apply the principles of energy conservation and change conservation to analyze electric circuits. In this lab, we will predict how circuits behave when resistors are connected in series and parallel. We will use multimeters to measure currents and voltage differences in circuits, and we will investigate the behaviors of resistors and capacitors. The materials and tools that we're using are ammeters, voltmeters, wires, batteries, and light bulbs. And the results that we found are that the voltage over a 47 ohms resistor drop was 0.631 volts, and the voltage drop over a 100 ohms resistor was 1.23 volts. The current that we found was 12.7 milliamps, and the total voltage of the batteries was 2.1 volts. The charging and discharging of a capacitor took approximately 10 seconds for a 10 ohms bulb and 20 seconds for a 20 ohms bulb. Here are some fundamental principles that we need to understand. Loop rule states that the sum of all voltage changes around any closed loop in the circuit equals 0. Node rule states that the sum of the current entering a node is equal to the current leaving the node. And Ohm law states that the change in voltage is equal to resistance times the current. Here's my initial circuits for part 1 of my lab. First, the circuit includes two batteries, which theoretically are 1.5 volts each, two resistors, one being 47 ohms, other being 100 ohms in series, and two ammeters around the battery. In part 1 of my circuit, the system was the circuit and the surrounding was everything else. I found that the battery had a voltage of 2.1 volts, which differs from the 3 volts that it was supposed to have. This is probably due to the fact that the battery was undercharged. The resistors were a 47 ohms resistor and a 100 ohms resistor in series, thus they could be added together to become a 147 ohms resistor. Using that, I was able to find the theoretical current, which was 0.014 amps. However, the actual current that we measured was 0.012 amps. The potential difference on the 47 resistor we found was 0.631 volts, and the potential difference of the 100 resistor was 1.23 volts. Those two added together and subtracted by the voltage provided by the battery, the total potential difference of the circuit was 0.139 volts. However, the theoretical potential difference of the entire circuit should have been 0 volts, as due to loop rule, the potential difference of the resistors should have been equal to the voltage provided by the batteries. Here are the resistances that I found for each element of my circuit. For the 47 ohms resistor, I found that it was actually 52.6 ohms, and the 100 ohms resistor was actually 110.8 ohms. The wires and ammeters should have a resistance of 0 ohms each. And here are some of the scenarios that I experimented with these circuits. First of all, when reversing an ammeter, it results in a negative reading as the current is flowing opposite to what the machine was expecting. Replacing an ammeter with voltmeter results in the ammeter having a 0 reading because the voltmeter acts as an open circuit preventing the flow of current. Replacing the voltmeter with an ammeter in parallel with the 100 ohms resistor results in the current increasing because the ammeter acts as a short circuit, thus the current would flow through the ammeter and not the resistor. Here's an image of me conducting the lab. In part 2 of this lab, we'll be dealing with RC circuits. The initial conditions are one capacitor, 10 ohms and 20 ohms bulbs, and two batteries. I found that when connected to a battery, the bulb does not light up. However, when taking the battery out of consideration, the charging and discharging of the 10 and 20 ohms batteries take 10 seconds and 20 seconds respectively. This is due to the fact that the equation for the time needed to charge and discharge is T is equal to RC. R in this case is 10 and 20 ohms respectively, and the C is 1. Some possible errors that could have happened in this lab are measurement errors with the ammeter and voltmeter, as well as the fact that the capacitor could have been charged from previous uses. Now I'll be answering the question of, what if I charge a capacitor with no resistor in the circuit? Removing the resistor makes R equals 0, so the time needed to charge and discharge a capacitor would be 0 times the capacitance, which is 0, and the capacitor will charge instantly. In reality, the battery, ammeter, wires, and capacitor itself all have internal resistances, preventing infinite current and giving a non-zero effective R. Therefore, the capacitor charges over a short time, and the ammeter reading shows a large initial current that quickly decays to near zero.